Hi, I'm Niccolo Battezzati from Argotec, and I'm going to present Agile Principles for Space Products, lessons learned on a software-defined radio for deep space applications. This is the outline of my presentation. First of all, a brief introduction. Then we're going to understand what is the Argotec's Deep Space Software-Defined Radio project and the lessons we have learned from this project. And then I'll draw some conclusions. But first of all, how we get there. So Argotec is an Italian company that is involved in the space sector. And since 2015, Argotec started working on deep space small sats. Later, last year, two of these small sats, Argomoon and LichCube, has been launched with the Artemis 1 and DART missions. Around 2020, Argotec started working on an R&D project for a deep space software-defined radio for its internal developments. And almost at the same time, we also started embracing Agile principles and practices. In particular, Agile was born in the 80s, 90s from the software community as a sort of new practice for a new way of working in the software. And nowadays has been acknowledged as one of the very beneficial set of principles and practices in the software community, but not only. Among its benefits, we have an increased adaptability of the software, that it is also important in uncertain conditions like space missions and non-recurrent designs, like deep space spacecrafts, and an enhanced software quality through continuous testing and integration, as well as regular review and refinement of requirements. So it started wondering, what if we apply these principles, these practices, to a whole space product? Well, as I told you before, Argotec was building a deep space software-defined radio. That is a project called Hermes, and it is composed by several hardware boards. We have a digital processing board, we have a power supply board, different radio frequency front ends. On the digital processing board, we have an FPGA that embeds a fast version of the DSP algorithms for the communication link and a software stack for the data link layer. So you can understand that there are many domains involved in this project, from software, FPGA, hardware, telecommunication, mechanics, and so on. And it's also a challenging project because of the features we want to achieve, like a high data rate, up to 100 megabits per second, multi-channel and dual band, the possibility to have a direct-to-Earth or a proximity link for moon communication, and a full configurability of all the tunable parameters and algorithms on the radio. So we started applying Agile at the whole product, and we learned some very interesting lessons that I'm going to share with you. Every lesson comes from a problem that we had to face, and in a certain way, we overcame learning something. The first problem we encountered was that the product vision was unclear. This is why business and engineering were in a certain way disconnected. Stakeholders of this product were not completely involved in the project. Priorities were not clear, and the team, as a result, was a little bit unmotivated. So what is the lesson we've learned here? It is that we have to make the product vision explicit to both the team and the stakeholders. How? Defining a clear product goal. So starting to understand the vision, define a product goal, and repeat this goal frequently, make it available to everybody. For example, hang it on a wall and where it can be seen by everybody, repeat it at every meeting, and so on. And also build a product roadmap, like a path toward this goal. As soon as we started speaking with the stakeholders to understand the real vision behind the product, we also understood that the stakeholders were disagreeing on the product vision. This is because they were not sitting at the same table. And this brought continued change of goals and a continued change of plans, because somebody were saying something, some other person was saying something different. So the lesson here is that representatives of the stakeholders shall sit together. Well, this has been a difficult point to achieve, and we did it creating a so-called customer team. This is an internal project, so we have not external customers because it is an R&D product. And so the customer team is composed of internal people that tries to understand the market, and they represent the stakeholders. And then the team involved this customer team in every product review, trying to make frequent reviews like 1 to 3 months, and defining the goals together with the customer team. This brought to a shared product vision for everybody. But started working, we also encountered another kind of problem. The fact that hardware and software team, as well as the communication team, were like different silos. So they were running on parallel trails, and they were not being connected. And this brought the fact that delaying hardware and software integration could hide design issues. And bugs are found during the final part of the test. We have no working product till the end of the project. There is no communication indeed within the team, and also hardware software design is not coordinated. The lesson here is we have to do hardware software integration at each product increment. So we built a cross-functional team with people coming from all the involved domains. So we have software engineers, hardware engineers, telecommunication engineers, FPGA designers, mechanical engineers, and so on. It was not so big team. There are like 9 to 10 people depending on the moment of the project, but they worked always together. We planned product increment every 1 to 3 months. And we also started using hardware breadboards if needed, if final hardware were not available. But we needed to do continuous hardware software integration. Well, as soon as the team started working like this, we found another problem. They were focusing on the system and not on the product. So the customer needs were not clear at this point. They were focusing, and we all together were focusing more on system requirements than on product requirements. And so this was very difficult to build product increments. Hardware-software interactions were hidden by this. So here the lesson is write user stories. They increase the awareness about customer needs. We started defining personas, like stereotypes of the customers, and define user stories for each customer. User stories is very easy way to write requirements, but focusing on the needs of the customer. So as a customer, I need this feature because I need to do this stuff. Also, going to the technical tasks, we understood that this was a critical point. Technical people were focusing too much on the technical goal of of the product. Let me make an example. I'm designing the file system of the radio. So I'm very focused on the characteristic of the file system, on the performance and so on, but I lose the sight about who is going to use this file system. Which one of my colleagues, a software engineer maybe, have to use this file system? What are the interfaces he really needs? What are the features he really needs? So here the lesson is again, team members should work for each other with a customer provider mindset. User stories can again help here, and write user stories for technical tasks too, as the colleague of yourself is your customer. Teammates are customers. This brings to a clear interface design. Well, then we encounter one of the never-ending problems with embedded systems. Hardware takes time to be built and software comes late. Well, we all know this problem. If software is developed after hardware is ready, this is very late in the project. We have less time for software testing, and also hardware is designed with no software awareness. The lesson we've learned here is that we need to start writing code on day one. Start designing, developing, and testing software immediately, even if hardware is not available yet. How we did that? Well, we started using emulators like QEMU to emulate our CPU. We created or found simulators for our overall system, or we use model-based design for creating models of the system used for testing software. Everything was related to this goal. Start writing code on day one. Well, hardware development takes time because of the production and procurement of components. And as in space, this comes even harder. For deep space missions, we often had to procure radar components, rad-tolerant components, and this had a huge lead time. This brings problems not only to software, but to hardware itself, because there is no room for mistakes. You have to do it right at the first time. Testing on real hardware comes late. Architectural issues evidenced during this test can require a very hugely costly rework. So the lesson here is early prototype with breadboards and commercial components. We started working with commercial dev boards. So we assembled dev boards to test and verify our high-level hardware architecture and to start writing software. And then while designing PCBs for space, we also try to reduce lead time buying commercial off-the-shelf components, also buying radar components, but also buy COTS components and mount these first PCBs with COTS components, adapting them to the new component in order to have the first prototypes early, test them, test the functionality, and test the software. Again, another problem like this is the FPGA. It takes time, less than hardware development, but more than software development. Because synthesis and implementation takes time, structural simulation is low, testing on hardware is even slower. And in the end, the risk is that bugs are found only when we make the integration with software. The lesson here is design modular architectures and anticipate testing. How? Using highly modular architectures, highly modular IP cores with standardized interfaces, and also doing development process like software. Write code, review, test, write code, review, test, like DevOps for FPGAs. Sometimes we lack tools that are really available for the software community, but we really try to be like software engineers. And also we try to higher the level, to increase the level of abstraction for testing FPGA code using behavioral test benches and also early prototyping with high-level synthesis. At the same time, deploying complex algorithms on real hardware can come again late in the project. And this is the continuous problem we had to face. We could not test algorithms on paper, of course, because they're a very complex one, and coding complex algorithm takes time. Also, if they are state-of-the-art or new algorithms, it took several design iterations to tune them to find the right way to design them. But at the same point, we have to de-risk this fact that we come late into the test phase. So the lesson here is design high-level models and simulate them. Model-based design can be useful to prototype, to simulate the algorithms, and to tune the models. And even if sometimes it's not feasible to make a direct translation to software or to the FPGA, even if tools are available, sometimes there is a lack of performance, we need to do manual optimization, but we can still use these models to verify our software or firmware. Well, the last lesson concerns requirements definition and software design. And the problem we encounter is that if we do this upstream for the whole software, we really increase the probability of deep refactoring. Well, requirement specification takes time as well as detailed software design. And the problem is that at the beginning of the project, we don't have the clear picture for everything in the software. And then also requirements change. You remember that I told you that the vision was not clear at the beginning, stakeholders were not on the same path, so goals were changing, plans were changing. This brought a sort of software rigidity. So we decided to have a very high-level architectural design with different layers for the software, really decoupled each other with abstraction layers in the middle. And the lesson we've learned is that it is better to define detailed requirements and detailed software architecture feature by feature. So starting from this high-level modular architecture, we started from the user stories. And for each user story, for each feature, we detail the requirements and the software design. And then we refined it by developing the code and testing it. So this brought, of course, to some refactoring, because at the feature level, we don't have the big picture. But in the end, having this very high-level modular architecture, all the modules then fitted into this architecture very easy, in a very easy fashion. So yeah, this lesson was an epiphany for us to define requirements and software architecture feature by feature. So to conclude, we really understood that R&D and novel products benefit from a fast iteration development cycle with frequent customer feedbacks. As you remember, we use this customer team. Then breaking down silos and creating cross-functional teams anticipate possible integration issues. Already when defining requirements, early prototyping for both hardware and software saves time on getting a product integration and testing phase, and decomposing by features instead of system components helps keeping complexity lower. So in the end, we can say that Agile principles and practices really came as a help for the whole space product we were designing, not only for software, where they are like best practice now, but also for the other domains that are not practicing Agile, like hardware, FPGA, telecommunication, algorithm design. Well, for all these domains, this principle and these practices can be helpful. So this concludes my presentation. I thank you for your attention, and if you have any question or feedback, please drop me a line at Niccolo Battezzati, Argotec Group.com. Thank you.